Okay guys, so now we're going to talk about specific ideal gas laws, and the first one that we'll talk about is Boyle's law. And Boyle's law states the volume of a gas at a given temperature and number of moles varies inversely with the applied pressure. So the way that I remember Boyle's law is if you boil water, the temperature stays the same. And in all these, except for Avogadro's law, the number of moles will stay constant. So here, if you increase the pressure, you are going to decrease the size of the container if it's a flexible container. So the volume of the gas will shrink. And so mathematically, we say PV, or pressure and volume, is equal to a constant. So they have an inverse relationship. This constant here, notice, will stay the same. The constant will stay the same. So if you increase one variable, the other one has to adjust or go down to keep that constant the same. I think an easier way of looking at it is if you are changing conditions and how you would work that mathematically. So here we say P1 V1, okay, is equal to P2 V2. So if you start with a given pressure and volume, and if you increase the pressure, then you can calculate the volume, the new volume of the gas. And so we'll do an example of that here in a minute. Okay, so here's our example. What is the volume of 40 milliliters of gas at 1.5, that should read atmospheres, if you increase the pressure to 3 atmospheres, temperature, number of moles being constant? So let's work that one out over here. So I always think it's helpful to write down your variables as you go. So what is the volume of 40 milliliters of gas? So that would be V1 would be 40 milliliters. And then a P1 would be 1.5 atmospheres. And then you have here, it says, if you increase the pressure to 3 atmospheres, so that would be P2, be 3 atmospheres. And then what would your new volume be? So that would be V2. Okay, so you just plug those in and solve. So it would be 40. I always think it helps to go ahead and write your units down as well. 1.5 is atmospheres there, is equal to 3.0 atmospheres times X, which will be our volume. So then that just becomes 40 milliliters times 1.5 atmospheres divided by 3 atmospheres. Atmospheres cancel here, and our final answer here will be 20.0 milliliters is our final answer. Okay, so there is a Boyle's law type of problem. Continuing on, let's talk about Charles's law. The volume occupied by any gas at constant pressure and the number of moles is directly proportional to the absolute temperature. So this is a little bit different. In Boyle's law, we had an inverse relationship of pressure and volume. So we increase the pressure, we decrease the volume. In Charles's law, we have a direct relationship. The volume is affected by the temperature directly. So the volume occupied by any gas at a constant pressure is directly proportional to the absolute temperature. So as the temperature goes up, the volume goes up, pressure remaining constant. Note the absolute temperature, so we must use the Kelvin scale. So that is an important note to make here. So you might want to underline, or you might want to highlight this absolute temperature variable. That means we have to use the Kelvin scale when we do our calculations. V over T is equal to a constant. So if you have a constant here, if V increases, T also has to increase as well. And I think it's also helpful to note this formula when you have variable conditions. V1 over T1 is equal to V2 over T2. And we'll use that to work our problem that we have. Okay, so here it says, what is the volume of 200 milliliters of a gas at 25 degrees C? All right, so here we have a V1 here, right? Let's use a different color for that because it's not showing up very well. We'll use red, I suppose. V1, right? And then we have T1 here. If you increase the temperature to 40 degrees C, so that's T2, right? So V2 would be what is the volume there. So let's write our V1. So our volume here, V1, is 200 milliliters all over T1, which is 25 degrees C, but we'll need to add 273 to that. So it'll be 25 plus 273, right? Gives us 298 for our Kelvin temperatures. Remember, we have to convert it to Kelvin, so we'll have to add 273 to that. V2 is our what we're solving for. T2 is 40 plus 273, and if you do that, you get 313, I believe. All right, and that would be K. All right, so then we'll cross multiply here and then divide. So you end up with K. Notice here that the Kelvin will cancel and our final answer will be in milliliters. And let's write that above my picture here. 210.1 milliliters was what you'll get. Milliliters is our final answer. Okay, easy cheesy. Little algebra there to get to the right answer. Cross multiply and then divide. Gay-Lussac's law: the pressure of any gas given constant volume and number of moles is directly proportional to its absolute temperature. So here we're given constant volume and we're dealing with pressure and temperature. So here the constant, so if pressure increases, so does temperature to maintain this constant value. And our formula is P1 T1 is equal to P2 T2. Oh, I needed to mention that you can also look at it as final and initial as well. So the final pressure and the final temperature would equal to the initial temperature and the initial pressure as well. Let's do a problem. Why? Because they're so much fun. All right, so it says here, what is the final pressure? So that is going to be our P2, right, of a gas at 760 torrs. If the temperature, 760 torrs would be P1, right? If the temperature is raised from T1 to T2, right? Because the 760 and 25 go together, and then the P2, the final pressure, would be with an increase in 35 degrees C. So let's work that out. We've got P1 here is 765 torrs. Same thing as a millimeter of mercury, right? Over 298 Kelvin is our temperature. So that's 25 plus 273 is equal to P2, which is our what we're solving for, and then 35 plus 273 gives us 308. All right, so that's going to be those two guys together, right? So it would be 765.0 Kelvin. So the Kelvins will cancel, and our final answer will be in torrs, 790.7 torrs. Answer there. Okay, very good, very good. Let's see what we got going on next. Lots of fun doing gas laws. I believe what we'll do here in the next slide is do what we call a combined gas law problem, combined gas laws. And the formula for this just combines all the different gas laws. So you have all the variables changing here, and you have to figure out the one thing the one second variable here that we're trying to solve for. So fun. These become more of a record-keeping nightmare than anything else. And so I'll show you how I kind of do it to make sure I keep everything straight. And you can do it however you'd like, but I think it's you do well to always put your units and your final answer if the units don't cancel out to get what you're solving for, then you're in trouble. So this one says, what is the pressure? So we know that we're solving for the second pressure. So here we have 500 milliliters. Let's do that in black because that will be our first volume. 1.5 atmospheres, that's our first pressure. And 280 kelvins. They gave it to us in kelvins. That's nice. That will be our first temperature because we always have to have kelvins, and they gave it to us, so that's cool. And it says here, if you raise its volume, so V2 here would be 600 milliliters, and we're solving for P2, right? That's P2 here. We're solving for pressure. If its temperature is changed to, or increased here, to 400 Kelvin. So that's our problem. Sometimes I think it almost helps to do your algebra with your letters and then plug in. You know, V2 is going to come down here and T2 is going to go up there. So it becomes P1, V1, T2, all that over T1, V2. All right. And that will give us our second pressure. So P1 is 1.5 atmospheres. 1.5 atmospheres times V1, which is 500 milliliters, times T2, which is 400 K. All that divided by T1. The first temperature given was 280 K, times V2. The volume was 600 milliliters. Okay. So now let's cancel out our units and then check the unit that's left over to make sure it's what we're solving for. So here Kelvin are going to cancel out, milliliters will cancel out, and then our final answer will be in atmospheres. Woohoo! Very good, right? That's always helpful. And so let's see here, I think I worked that out, and our answer is 1.8 atmospheres. All right. So this concludes the third recording in Unit 9, Gas Laws, and I hope you find that to be very, very helpful indeed. And then in the next recording, in Recording 4, we're going to cover some more advanced types of concepts. We'll combine Avogadro's law with the ideal gas laws that we've already covered to make what we call the ideal gas law formula. And in this formula, you can change masses of gases into liters of gases. And you can also work some stoichiometric problems under non-standard conditions. And we will do that in the next video. So looking forward to seeing you then. Hang in there. Know there's a lot of work to be done on this. Do your practice problems. You can do them as you go along as we explain them. Or you can wait to the very end and use your notes as a review type in case you get stuck. So looking forward to seeing you in the next recording.